So previously we have gained the knowledge of matrix theory and differential calculus. So these two knowledge will be useful somewhere in the unit 3. So today we'll be discussing about definitions and all other things, basic terminologies for differential uh, equation, ordinary differential equation. Okay, we'll not be solving much problem. So these definitions are important because we have to understand what we are going to do. So starting from that, since this is very important for engineers too, modeling of a physical problem using the mathematical equations. So whatever physical problem you get, you need to represent it in terms of mathematical equations. Starting from the maximizing the production cost of a semiconductor device. So not maximize, it should be minimizing the production cost of a semiconductor device. Okay, and that's a physical problem. You make it that equation you have seen that in the last class we have seen maximize or minimize effects. So f can be summation. It can be there are many components can be there subject to the constraints will be there. So these are the equations, mathematical equations will be there. They should satisfy this equation, and based on that you will be discussing the solution of the system whether the device is actually feasible, whether this is profitable or not. From that equations you can get the direction. Okay, now the differential equation, it has many applications. For example, to calculate the temperature, pressure, displacement, velocity, stress, strain, and concentration of a pollutant with the, of course, these changes will be calculated with respect to some other variable, for example time or location. If we talk about location, then it is actually related to the coordinates xyz. So both would can be required for the differential equation. Now for a motivating example, if you throw a ball from here, you need to I think most of you have, all of you have studied the motion of the projectile. What would be the velocity so that uh, it, it will cover at a minimum distance. So here x dot is actually dx dt. This is a Newtonian notation, x dot, and dy dt is nothing but y dot. So here we have differential coefficients. For example, rate of change of a variable or a two variable with respect to one variable. So here t is independent, x and y are dependent variables. If you think about the inflow and the outflow of a container, okay, then the differential equation arises of this form. So whatever you do, this is a physical problem. You are modeling this physical problem in terms of mathematical equations. So whatever you do so far, in fact in your BTech course and after BTech also, you need to represent the quantity in terms of mathematical equations. Otherwise, they will not make any sense. Now, if you think about another real problem, to find out the stress or the stress or the strain, different points of the, so you need to calculate Wx. So Wx is the distributed load distribution on the bridge, which is hanging over the two, for example, two cities, they are joining. Okay. So then there is differential calculus. In fact, here you need to run differential equation. So what it means actually, the differential equation. Okay. People might ask you, Many of the students, I have seen some of the students, in fact, many students, they can say that, sir, I know how to solve a differential equation, but I don't know the definition of a differential equation. So, if this is the case, so we'll start with the definition. So, what is the definition of a differential equation? It is an equation containing the derivatives of one or more dependent variables with respect to one or more independent variables. So it is a then we call it a differential equation. So which means this is a function. If you can say it is an equation which contains the derivatives of the dependent variable and with respect to one or more dependent. So in this case, only one independent variable. So this is, you can say, f1 x y, and then you have, it is a function of dy dx equals to 0. Similarly, you can write this is as f2 some function. It is an equation contains x y dy dx and then d2y dx2 equals to 0. So if we have ordinary derivatives, then we call it an ordinary differential equation. But if we have partial derivatives, then we call it a partial differential equation. For example, here we have x. These are dependent variables. So let us write first independent. First is x and y are independent variables. Then there can be function of u, and also we have del u, del x, del u, del y equals to 0. So that is one another differential equation. Okay. Now, if you remember the function that rate of change of derivatives that we have seen earlier, so for that we have to recall the thing that we have to how these are actually related to our physical problems. If you remember this problem, that the coefficient when we change x, y, and z, see that as the rate point is actually moving, there the value x, y, and this f of this is dh. In fact, this is h and t. For example, t is h and dh dt. So that's a differential equation for this case. Now, if you consider when x, y, and the derivative change, when t and h changes, we see that the equation will also change. In fact, if you when satellites are projected, what would be the uh, injection velocity of a satellite? At a different point, it will take some different values so that it will overcome the gravitational force, and then it will come to one orbit. Okay. For example, what could be the velocity the injection velocity of a satellite, because you want to inject one. In fact, this is a rough idea, although this satellite injection is actually, it's a very complicated problem. But roughly speaking, there also they use the concept of ordinary differential equation, or in other words, differential equation, because there will be many independent variables and many dependent variable. In that case, we will introduce the concept of partial differential equations. So they will be used. So by the derivative, we can classify our differential equation into two. So differential equation, one is ODE, ordinary differential equation, another is partial differential equation. Okay. Now, whenever we have one equation, we want to think of the solution. Whether the equation has a solution or not, that is our point of interest. Now, whether a differential equation has a solution or not, that for that we need to give some evidence. Under what condition the equation will have solution. So that is very important to study. So for that we need to define the, we need to know the Ellipsis condition. So Ellipsis condition is there. A function is said to be satisfy Ellipsis condition with respect to y in the real line over the domain if there exists a constant L greater than 0 such that it will satisfy this equation, this inequality. In fact, this is actually denoted by, if you divide by this, uh, for example, if you divide by this y1 and y2, then it denotes that actually x is fixed, so the y, so derivative actually it will derivative will be bounded. For example, if you think of f of uh, x equals to sine x, this is a ellipsis function actually. Those functions which satisfy ellipsis condition, they are called ellipsis function, and f dash x is minus sin x. Sorry, this is cosine x. F dash x is cosine x. Okay, so this is bounded by 1. Okay. If you think, so here L will be 1. If you think of these 2 points, two different points, and then take another 2 points, then this. In fact, ellipsis function are those functions whose derivatives are actually bounded. First order derivative is bounded. Okay. These are two examples. This function will not satisfy on this interval. But if we change the interval, or if we can extend the interval, then it may satisfy the ellipsis condition. So the existence and uniqueness of the theorem for a ordinary differential function, ordinary differential equation. So for example, this is our ordinary differential equation, dy dx equals to f of xy, where y of x naught is equals to y naught. That is given. One initial value is given. Okay. If this is the case, and if we have the region, that is the point of the region of our interest, in which region we want to find out the solution. Okay. Then, if it satisfies, if f of xy is satisfies the ellipsis condition with respect to y, then there exists a unique solution. y equals to phi of x continuous on this interval such that it will also satisfy the initial condition where h equals to this. So this theorem guarantees the existence of a solution to a differential equation provided initial value is given. So if we don't know the existence of the solution, for example, if you get the differential equation without knowing the existence, you are going to solve this problem. Then you may lead to wrong direction. So that is why for any equation you solve, you must know the existence and the uniqueness of the, not only it may have many other solution, but existence should be verified whether it has existence or not. Okay, so with this theorem we will move to classify uh, or study the different types of differential equation. For example, in fact, some of the topics will be repeated from your school level mathematics. For example, yeah, if we have one independent variable and one dependent variable, then we also call it a ordinary differential equation. For ordinary differential equation, we will have only one independent variable. See here, this t is our independent variable, but we can have more than one dependent variable. Here, x and y are dependent variable. But if the number of independent variable is more than one, for example, two or more, then this function, this equation is called partial differential equation. Now the order of the differential equation, just to recall, the highest order of the derivative, that is the order of the differential equation. So here the highest order is 2. Although this power is 3, will the order of the differential equation is actually it depends on the order, highest order of the derivative. For the other problem, here the highest order of the derivative is 4. So here is fourth order partial differential equation. This is second order ODE. Now, a differential equation, a first order differential equation, can also be written as of this form, because we have only dy dx equals to, for example, m by n, some functions. Then we can write in this form also. This is another approach. Now the degree of the differential equation. The degree of the differential equation is actually the degree of the highest order derivative. So that's for the above equations. See, the degree is 1. So highest order derivative. This is a second order derivative. It has power 1. Here, the highest order derivative is second order derivative, and its degree is 1. But here, this is first order derivative, but this is second order derivative. So the degree is actually 2 here. So degree of the ODE or degree of the PD also. We can define same way differential equation. Degree of the differential equation. Now, how do we formulate differential? No, this is a differential form of the first order D. In fact, as I have mentioned that m dx plus n dy equals to 0. So this form is known as differential form because there is no reason. In fact, just a name, giving some name to the differential equation. If you can separate them, these variables, or if you can write first order derivative in terms of this form, then we call it a differential form. Now, the general form of the differential equation, nth order ordinary differential equation in one variable. For example, x is our independent variable, and we have n nth derivative continuous. Then we have this is first order. Then we have second order derivative, and then we have nth order derivative are continuous. Okay. Then this equation is known as this is a general form of this equation. For example, you can see here this is first order, this is second order, and this is nth order differential equation. Now the normal form, as you can, the normal derivative by solving the derivative dy dx, the normal form of the first order differential equation is given by of this form. For example, this is our given. So from here we need to separate the dy dx coefficient. If we can write in this form, then it is becoming normal form. Similarly, here for the second order differential equation, so this is for first order differential equation, normal form. But here for the thing is we need to separate the highest order derivative. So here the highest order is 1, here the highest is 2. So in the left hand side we will write the highest order. Now linear, okay, for classification by linearity. So for example, if this is the given differential equation, okay, then we call it a linear if all the power for the function, that is y dash, y double dash of the nth derivative, if its power is 1 and the coefficient function are independent of y. That means here you cannot give here you cannot take a of y, or for example y square or y prime. Okay, these functions are not like this. So if these two conditions are satisfied, then we call it a linear differential equation. So that's very important. That's very important observation, because many times we students make mistake on the linearity. If the degree is 1, then we call it linear. So that is not true. So that is not the actual definition. The actual definition is all the degree of all the functions related to y. That means y dash, y prime, yn, any derivative. Their degree will be 1 and the functions will be independent of y. They are functions either they can be constant, they can be function of x. There is no problem. But if this is the function of, so for example, e to the power y or sine y, in fact, or sine x also. No, sine x can be there. Sine x can be there. Sine y or e to the power y or y square. Then we call it a non-linear. So that's very important observation. So for linear and non-linear functions. So these functions cannot be this these coefficients They cannot be functions of y. And the degree for these functions will always have 1. Here also 1. We are not talking about the right hand side. Yes, yes, we'll discuss about the Bernoulli's equation after some time. Bernoulli's equation will be, it can be linearized. We can make it linear form. Okay, it will come into the picture. Wait for it. Maybe in the next class we'll discuss. Okay. So linear and non-linear examples, differential equation example are there. So the first equation you can see linear equation. All these are linear equations of order first. This is first order linear equation. This is second order linear equation, and this is third order linear equation. But if you look at the nonlinear terms here, 1 minus y into y prime. So that means that a function, yeah, the coefficient of the y prime is y, so which is a function of y, which is not a linear. Similarly, in place of y, we are having sine y. So this is also non-linear. Not only that, if the power is also more than 1, so then also it is non-linear. So that's very important observation, or you can say these are important characteristic of the linear and non-linear differential equations. So how do you formulate linear ordinary differential equations? Formulation of linear for a given function. These are the given functions. So how do you formulate? Eliminate the arbitrary constants. So how do you eliminate? If you differentiate this function, then you will get this. Now, in place of a, you substitute these functions, then you will get this ordinary differential equation. So that is one observation, that by elimination of, if we have two arbitrary constants, then we need to go for second order partial different derivatives. Earlier we have seen only first order derivative is sufficient to eliminate the variable, eliminate the constant, arbitrary constant a. But here we have two arbitrary constants a and b. So that is why we need to go for second order differential equations. Here we have three arbitrary constants, so we need to go for three third order derivatives. So here, so third order derivatives. So this is one another equation. So for formulating, we need to go for. There are some problems where instead of this arbitrary constant, we need to eliminate the arbitrary function. Now it is time to discuss what is the meaning of a solution of an ODE. Now, as stated above, our goal is to find out, to solve the equation. That means to find out the solution of the differential equation. Okay. So that is why we need to define the solution. So any function, for example, phi, is defined on the interval I, possessing at least n derivatives. So this is phi, phi prime, first order derivative, then we can have phi of second order derivative, and then in this way nth order derivatives are equal. Now if you substitute in the function, in the equation, the differential equation, and make it 0, In fact, without this 0, it is not a differential equation. So that are continuous on this interval, which is when we substitute these values on this equation, then the nth order differential equation reduces the equation into an identity. Then it becomes a solution of the equation on that particular interval. For example, phi can be solution on an interval I1, but it may not be a solution on the another interval for the same differential equation. So that is why this interval is also important, and at the same time the function, it is also important. Which function you are talking about and which interval we are talking about. Normally, we will denote the solution in place of phi. We will write the solution as y of x for first order. In fact, this is more popular notation. Now, this is a function versus the solution. So, when do we have y equals to 1 by x not equals to 0? So, this is a function. The graph of the solution f of an ODE is called the solution of the graph. Solution of the curve. Okay, the graph of the solution f is called is an ODE of an ODE is called a solution curve. Since we are assuming f is a differentiable function and it's continuous on the interval I of the definition, where we are defining this except this 0, this function is continuous, because at x equals to 0 we have one asymptote, particle asymptote for this function. Okay, thus there may be a difference between the graph of the function and the graph of the solution. So function f and solution f are two distinct concepts. So for the function x, if you consider about the function, the domain of the function is the set of real numbers except 0. When the graph y equals to 1 by x, we plot the points on the xy plane. Okay. Then the numbers are taken from its domain. The rational function y equals to 1 by x is discontinuous at 0. Here it is 0, discontinuous. And its graph in a neighborhood of the origin is given in the figure. So this figure actually gives the graph of the figure. Okay. Now the function y equals to 1 by x is not differentiable at x equals to 0, since y has a y-axis, that is x equals to 0 is the vertical asymptote for this graph. So for this function we have a vertical asymptote, and we can say that this is not differentiable at x equals to 0. Now what is the meaning of a solution curve? So the solution curve y equals to 1 by x is also a solution curve to the first order differential equation, that is here. So the equation is actually, if you write it, x times dy dx plus y equals to 0. So this is our actually differential equation. If you solve it, then you get this is a solution. But when we say y equals to 1 by x is a solution of the differential equation, we mean that it is a function defined on an interval on which it is differentiable and it satisfies the equation. So you see the clear difference. Whenever you mention that is a solution, that means you are thinking of the this function also, the derivatives are also exist on the particular interval. Okay. Whenever we say y is a solution of this function of this differential equation, then we automatically assume that these derivatives will exist on the particular interval. So that is why there is a difference between the function f and the solution f. Function can be defined where the derivative is not actually, derivative does not exist for x equals to 0. And then solution f, it can be defined in several intervals. For example, if you think about the solution, the intervals that you take which do not contain 0, such as minus 3 comma minus 1, half comma 10, minus infinity comma 0, open interval, and 0 comma infinity. So all these sub intervals, so I can be like this. So on this interval, the solution f will be having this derivatives continuous. So for function, so because the solution curves defined on this interval are actually simply segment of the solution curves defined by the y equals to x on the whole, in fact, open interval minus infinity to 0 of this function. So it makes sense that we have to take the interval I to be as large as possible. So thus we would like to take I either minus 0 to infinity, sorry, minus infinity to 0, or we can have 0 to infinity. So that's how the meaning, the physical meaning, the geometrical meaning of the solution of a curve, of a solution to a differential equation. And then we just to recall, quickly recall these problems. I think you have studied them, but again, those who have not studied, just go through them. So differential equation with the first order and first degree. Okay. So here we will be discussing about dy dx plus equals to sum f of x y. The order is 1 and degree is also 1. Okay. This can be divided into 4 parts. 4 actually situations. So first situation is equation solvable by separation by variables. That means you will have x dx, m dx plus n dy equals to 0. That means you can separate them. There will be some homogeneous case, then linear equation with the first order, and then exact equation, exact differential equation. So what are those? We will discuss one by one. So today we are talking about the variables which are separable. So whenever we have fx, so dy dx, it is equals to, for example, f of, so phi of x by f of y. Okay, if we have this situation, then this can be written as f of y dy equals to phi of x dx. The working rule for this problem are simple. First, we separate them, then we integrate both of the sides with respect to x and y, and then we add one arbitrary conditions and arbitrary constant on the right hand side. This should be the integrating constant. So, for example, this problem, let us try to solve. If you try to solve this problem, then you will get, just quickly do it. So here we will get y sine y plus y cosine y times dy, and x can be multiplied. So x 2 logarithmic of x plus 1 into dx. So by separation, let us separate them. So integrate on both sides. Integration on both sides. We have sin y dy plus integration y cosine y dy equals to 2x log x integration plus x dx integration. So if you do it, then you will get, so for here you will get minus cosine y plus, this is integration by parts, you will get here y sine, just a minute, okay, y minus integration 1 times sine of y dy equals to, we have again 2 times, this is log x square by 2 minus 1 by x into x square by 2 dx plus, here it is x square by 2 plus some c constant. Okay, now you have, this is y sine y equals to, so 2 log of x into x square by 2. Okay, and we have minus x dx plus x square by 2 plus c. Next we can get, so let me just take another slide where you can write, so y sin x, so we have y sin y, yeah, y sin y equals to 2 into 2 logarithmic of x into x square by 2 minus, I have x square by 2 plus again x square by 2 plus c. So these two will get cancelled. So we have y sin y equals to, these two and these two gets cancelled. So x square logarithmic of x minus, that minus, here it will be plus. So this is our answer for this problem. Now for another similar example, you can solve it. Verify this example. What you have to do, we need to just separate them. So again, you try to verify these equations and also you verify these practice problems. So I'll stop here today. In the next class, we'll, in fact, I can give you that exercise also for homogeneous equation, since you have studied them. So go through it. Whenever we have homogeneous case, so the functions will be of this form. In place of y, we will substitute vx, then use the working rule and try to simplify and then solve. So yeah, if you try to solve it, then you will get, so put, let us substitute, this is 2x square 2xy plus x square into y, or if you can just In fact, this is dy dx. No, yeah, here it is. I have missed it. So this is dy dx. So there is a given problem actually. From here you separate dy dx, write it in the normal form. Left hand side dy dx, the right hand side is a function. So 3y square, 2xy, then 2xy plus x square. Okay. Then put y equals to vx. Then you get dy dx equals to v plus x dv dx. Now you substitute it here. Then you get v plus x dv dx equals to 3 vx whole square plus 2x into vx. Then again 2x into vx plus x square. Okay. If you simplify it, then you will get here it is 3v square plus 2v by 2v plus 1. So now we have dy. So v, we have v plus x dv dx, which is 3v square plus 2v by 2v plus 1. So here we get let us try to separate them dv dx. So if you take it here, you will get 3v square minus plus 2v minus 2v square minus v, and the denominator will be 2v plus 1. You take v out on the right hand side, then you will get these values. So here you will get this is nothing but v square plus v divided by 2v plus 1. So if you just separate them, the variables, so left hand side in terms of v, right hand side in terms of x. Here you will have 2v plus 1 by v square plus v into dv, and then we have dx by x. So if you take integration, take the integration, then you have 2v plus 1 by v square plus v into dv. Again integration dx by x. Okay, let us write down the constant c. Here you will get logarithmic of v square plus v into logarithmic of x. Okay, now equals to logarithmic of x plus, in place of c you can say logarithmic of c. You can take so that you can eliminate logarithm. So v square plus v equals to x into, or you can say write cx. Now in place of v, okay, now we have v equals to, sorry, y equals to vx. Substitute. So v equals to y by x. So here we have, so v square plus v equals to cx will give you y by x square plus y by x equals to cx. From here we get y square plus y into x equals to cx cube. So this should be our answer, final answer. So in this way you can try to solve the other problems also. Since you have studied these things, so this is for your practice, and then just for quick review, try to go through it, and we'll try to solve the next important topics in the Monday class. So if there are no doubt, you may leave the meet.